And I'm mindful that Rick is probably, well, he's in Canberra, and he just got there. So hopefully he's not too bleary-eyed to kick this off. So I appreciate him being willing to do this at midnight Australia time. So he's going to kick us off today talking about AI for science and the security workshops and the associated report. So Rick, over to you. Let's see if we can do you have slides?
Okay. You guys should see a screen.
Yep.
All right. All right. Well, thanks for inviting me to give an update on the AI for science work. Yeah, I did travel 27 hours, got a couple hours of sleep. Now I'm going to update you. So as you know, last summer, 6 labs organized a series of town hall meetings that were held in June, July, and August to take a fresh look at the opportunities in AI for science, applied energy research, and national security related work. These were led by myself, Jonathan Carter, Doug Cothe, Rob Neely, Jason Pruitt, and John Fedema from the 6 labs that you see on the screen here. And what this talk is, this presentation is a hybrid construct. It gives you a bit of an update on the report, and the report's out, and you can download it and read it and so forth. But it also frames where Office of Science and NSA have been thinking about taking the initiative. And we've used this deck in various briefings on the Hill and other places. So it's a hybrid kind of story. So let's start by talking about why this makes sense for DOE. So DOE has a pretty unique position, actually, globally, around the capabilities needed for AI leadership. So we have, of course, very powerful computers. We have an amazing array of scientific experimental facilities that generate huge amounts of data and that are complex and that have thousands of users. We, of course, are responsible for the nuclear security, and that involves very deep partnerships across other parts of the government. DOE is the largest producer of classified and unclassified scientific data, and that's the raw material, obviously, for training models to do work in science. We have a very strong foundation in the sciences, right, with tens of thousands of scientists at the 17 national labs. We have the largest scientific workforce in the world that's under one logical hat, and very strong ties with industry, both the technology industry, computing and related, but also the energy and other industries that are related to DOE mission. So it puts DOE in a very unique place, and that's one of the reasons why we've been so energized to work out a strategy for doing AI. Now, if you recall, back in 2019, there was also a series of meetings. These were held at 3 labs at Argonne, Berkeley, and Oak Ridge, and then a summary meeting in DC. That really took the first shot at trying to understand what the opportunity space was for AI for science. But then we had a pandemic. Of course, we had a wonderful report that came out of ASCAC subcommittee. Thank you, Tony, that recommended a major program. But then we had an election and a pandemic, and things kind of slowed down. But they slowed down in terms of maybe program planning, but they didn't slow down across the world in terms of advances in AI. And over this 3-year period, there was enormous progress, right? Large language models came onto the scene and took off. The use of AI to generate images, AI to fold proteins, right? AlphaFold 2 has now folded over 1 billion proteins. AI has been used to give hints to mathematicians to make headway on very interesting problems and create some new algorithms. Right? It's been used to automate enormous quantities of code generation through various plugins in GitHub and Copilot and so on at Microsoft. There's an explosion of new AI hardware. AI is being used to accelerate high-performance computing simulations. And of course, exascale machines started landing. So all of that was happening. And in lots of discussions with headquarters, we decided in the spring of 2022 to kind of reprise the landscape of discussions with the community in the landscape, to understand what these new opportunities or refresh the opportunity space. And that's the result of this workshop, AI for Science, Energy, and Security. And we changed the leadership to include the 6 labs, the 3 NNSA labs joined forces, and we held the meetings, 2 of them at HBCUs and 1 at a HSI. So they were at Memphis State in Memphis, they were at UC Davis, and at Bowie State in Maryland. And there was a very large number of people involved between the 2 sets of workshops. We haven't done an exact counting, but it's over 1,300 people that have been involved in the planning of these things. Now, we organized the second series of town halls quite differently. So the first one was organized kind of the way universities organized, right? We had topics in biology and climate and high energy physics and so on. And we also had cross-cutting topics, and there were, we kind of mixed people up, but there was no notion that there was some high-level structure of AI methods that might be gaining momentum that would be more universal. But for the second round, it became pretty clear to us that we had to put more structure into the discussion. And we came up with, the leadership group came up with these 6 areas, and we organized the workshops around these 6 areas by picking pairs of them at each of the 3 workshops, and then cycled through both the cross-cutting technologies and the targets for application. So let me just describe these briefly, because these are kind of at the crux of how our thinking has evolved in the last 3 years in particular. So the first one is this notion of AI for advanced property prediction and inverse design. The idea that we can train on large amounts of data, make forward predictions to assign properties to, let me say, materials or drugs or polymers or something like that, to make predictions where we don't have a grounded, say, mechanistic model. That's a forward case. But if you have enough data and the right kind of model, you can actually do an inverse design problem using the same machinery. And this is really the target here, this idea of training large models that could give us the idea of what materials, say, to make, or what molecules to make to have certain properties. So inverse design is very powerful, and it's a cross-cutting concept across DOE. The second one is this idea of combining AI and robotics to create self-driving laboratories, or sometimes called autonomous discovery-oriented laboratories. And of course, one class of targets for this are the traditional benchtop experimental sciences, right? Material science, chemistry, and biology, where it's very labor-intensive, very instrument-intensive. But we can also apply the same ideas to sample handling and things like light sources and neutron sources. So this idea of a closed loop where an AI, humans are giving the system some high-level guidance, and the AI is planning experimental campaigns, carrying out those experimental campaigns, ingesting the data, updating its models, and essentially organizing an entire series of experiments aimed at some objective is the concept here. It's a very powerful concept. It's got a lot of momentum in other institutions. It's a particularly hot topic in Canada and the UK. But it's one that we think is poised for changing how DOE does science, experimental science. The third one is one that many of you are already quite aware of, is this idea of AI-based surrogate models for high-performance computing. So the concept here is, instead of doing traditional handcrafted reduced order models, say, to search a large parameter space, say in reactor design or material science, the idea here is to use AI to automatically construct a machine learned kernel that replicates the essential behavior of a PD-based system or ODE-based system, and then use that in conjunction with the original model, perhaps, to make a very powerful system to accelerate search or to accelerate collections of ensembles. And this has been done already in many fields: density functional theory and climate, in biology and drug design, and so on. And this has the potential of really changing qualitatively the science we can do. If you can accelerate a climate code by, say, a factor of 1,000, which of course hasn't been demonstrated yet, but if you could do that, now you can use an ensemble in a case of, instead of a single instance of a model, and that could allow you to get a better handle on uncertainty and so forth. So it's a technique that couples with exascale to really accelerate applications. On the lower left here is this idea of AI for accelerating software development and programming and software engineering more generally. And of course, many of you are very aware of this, but there's a huge application of AI in either translating codes, generating codes, debugging codes, optimizing codes, not just in classical computing, but in quantum and so forth. So that area, I mean, we talk about this as DOE being powered by software, and this is a technique of applying AI to the core of what it means to be productive in many areas. The next one is this notion of AI for control of complex systems. So many systems that DOE is building or operates as facilities are very complex, have a very complex classical control systems, but there's a movement towards doing better than classical control systems by using AI systems that can be co-trained with, say, simulation data or historical use data. And this could be in a fusion reactor to steer it, to avoid disruptions. It could be in an accelerator to keep it in the sweet spot. It could be in something like the power grid or other complex systems. So this notion of AI in control, and particularly in complex engineered systems, is the fifth one. And the sixth one maybe is the foundation of everything going forward, perhaps. But it's this notion of foundation models, right? So clearly foundation models are having a huge impact in language and in image-based systems. But we think that foundation models could be the basis for many, many kinds of applications in DOE and moving towards supporting of things like hypothesis formation. So let's just drill down a little bit. So the report has got, it's 200 plus pages. It's got lots of examples in these 6 areas mapped against the domains of DOE. And in the bigger version of this deck, there's 2 dozen slides that go on the back that actually walks through each of those sections. I'm not going to go through that. We don't have time, of course. But we're going to dive into one, and we're going to focus a little bit on the foundation models. So foundation models, this term was coined by the group at Stanford, but it basically refers to any kind of model that's trained on a very large collection of broad data. And it could be multimodal, doesn't have to be just text or images or something, it could be multimodal. It's pre-trained on this and then has a variety of techniques applied to that model to adapt it to downstream applications. And the original formulation of this a few years ago, this notion of tuning or somehow producing specialized versions of the models for many downstream tasks was inherent in it, although that may be changing. It's often the case that you get a base model and then you have to do some additional work, say, to make it useful for interacting with humans. So that's done, for example, with ChatGPT, with alignment work, with reinforcement learning, with human feedback, and so on. Large models exhibit emergent behavior. As the models went past 100 billion parameters towards, say, 1 trillion parameters in something like GPT-4, they can carry out many kinds of tasks with skill levels that are very impressive that they weren't explicitly trained on. And this idea of emergence is really fundamental here. It's what's make these models very powerful. But also the idea that you can build hundreds or thousands of applications sitting on top of them. So you're building a whole new ecosystem. The question for us is how to use this technology in the context of science and what has to be done to it to adapt it to science. So some of the kinds of tasks that these models can do and that are already being used by folks at the national labs and universities supported by DOE are listed here. So for example, this idea of using a model to summarize and distill knowledge. You could think of this as going from unstructured knowledge that the model was trained on, say, through texts or papers, and producing structured knowledge out of it that could be then input to other kinds of computer programs. This is being done in protein interaction networks and materials compositions and code kernels and so forth. So this idea of distillation, knowledge distillation, is very powerful. Another one is synthesis. So these models can synthesize across the wide variety of literature. This allows them to do things like write code in things that they weren't explicitly trained on, or to do derivations in physics, or to summarize a paper in the context of, an approach in another paper. They can also generate plans, solve logic puzzles, write experimental protocols. People are using these to generate code for robots and so on. On the right-hand side here, just as an illustration, I was making some slides, a few weeks ago, and I asked the model, GPT-4 what languages it felt comfortable generating code in. And it made this giant list. I edited it off here at 19, but a very powerful set of languages that it's pretty good at generating. It doesn't always generate the right code. Sometimes it gets APIs wrong because of the cutoff dates and things have been updated. But if you're somebody who codes a lot, you're probably already using something like GPT-4 to improve your productivity. And plus, it's a lot of fun. But there's one more thing that I think is very important with these models. We're trying to understand, are they moving to the role of an assistant or as an AI colleague? And there was a fascinating paper that was posted on the archive a couple of weeks ago on the right here. I'm trying to remember the title here. It says, can ChatGPT be used to generate scientific hypotheses? And of course, this was one of the use cases that in the workshops we hypothesized about, that a sufficiently powerful model like this could be useful as generating hypotheses. So there was this group at MIT, and Weitzman spent some days. These are folks in materials chemistry, quantum information, and they engaged in a series of experiments with ChatGPT-4, basically getting it to dialogue around open questions and around hypotheses. And they made a deal among themselves, the crew, that they would consider the experiment a success if at the end of the week, they wanted to invest some of their limited experimental time and experimental facilities in pursuing some of the hypotheses that the model came up with independently of their own work. And they include a lot of the examples in here, but then they write this summary statement. They say, well, after experimenting in our own research, et cetera, we find that ChatGPT-4 is knowledgeable, frequently wrong, and interesting to talk to. In other words, not unlike a college professor or colleague. And and I think this was maybe a little light bulb going on in people's head around this. This is early days in AI, and it's already becoming sufficiently interesting that people are spending time in it, not just playing around, but actually spending time and thinking about what's coming out of it and whether it's powerful enough to invest their own experimental resources. So the question is, with sufficient work and engagement, could we develop a system that would be a very powerful assistant for theory? And I think the thinking is this may very well be possible. Let me try to get my, all right. So the workshops, really pulled together major opportunities. It wasn't an attempt at building priorities. It was an attempt to scope out the big opportunity space and talk about where DOE possibly could go. Sorry. So we organized the opportunity space really around these three big thrust areas that DOE is responsible for, right? In science, energy, and security. And you see some examples here, controlling fusion reactors, porting scientific codes, in energy, optimizing things, manufacturing processes, microelectronics, and so on. And in national security, many opportunities there as well. Now, this slide here talks about kind of the positioning that's happened since the report has come out. So obviously, there's been a lot of discussion about the risks and opportunities for AI broadly. And we put these two categories of risks together to try to guide a conversation. So what's really needed globally, right, is this notion of a responsible AI that's aligned with human needs, human values, and is trustworthy. And We think that this is something that DOE also needs, right, to execute our mission in science, energy, and national security. We need a responsible AI, one that we can trust and one that we can use in various ways to advance DOE mission. In the process of building such AIs, we think we can contribute to these two classes of risks that are currently being discussed. And mostly the societal risks that are being discussed are really on this left-hand side, right? This notion of general society AI risk, an AI that might be really good at doing deep fakes or generating disinformation, or that might be able to get in a tight loop with social media to do behavioral engineering and so on. So we think that the general techniques that we have to develop for doing science are very likely to be able to contribute to those risks. But on the right-hand side are larger scale, maybe risks that are not being talked about so much. These are things where AI in the hands of a bad actor could be used to create great harm. And I won't go through these in detail, but just saying that DOE, for lots of reasons, has expertise that's relevant to these problems on the right-hand side. And we believe that any integrated program is going to have to take a look at how we might use AI to understand what's possible on that side as well. So DOE is well positioned to be the leader in the US government for trustworthy and responsible AI R&D. DOE is probably not the right agency to be the lead on monitoring and regulation, but being the organization, the R&D organization that can really drive, because we have our own mission needs for trustworthy and responsible AI. And the country needs this for reasons beyond what we need it for. And so if we can make progress on these issues, we think we can contribute significantly to the national landscape. So how do we summarize this? Well, we summarize the rationale for DOE here is by saying that we've got a need for responsible AI driven by our mission, science, energy, security needs. We've got this world-leading R&D expertise and a very strong history of large interdisciplinary teams, which are essential for building leading-edge AI systems. The world-leading groups have teams on the order of 1,000 people building these models in each group, and we know how to put teams together like that. We just are coming off of a 7-year, close to $2 billion project in the ECP, and we know how to organize our community this way. And we're very uniquely positioned because we have the exascale systems, the strong ties with the technology and energy communities to work on this. So in a summary, I mean, the pitch that we're making is that only DOE and NNSA can really advance this responsible co-design of AI R&D with a strong focus on science, energy, and national security, and tie it to our mission and creating and building very powerful solutions. So kind of in summary, the AI for science, energy, and security activity, the report, it builds on our previous community input, and it gives us kind of a blueprint of where we could go. It's not an implementation plan. I think that's coming next. But it's very clear that we can leverage our experience with large-scale integrated efforts, such as ECP and the hub-like centers, these large-scale super centers that DOE is really good at running to bring those combinations of skills together. Now, this is my last slide, and it's just and I'll switch it over to questions here in a second. This is kind of where we are at the moment. So we're imagining a new initiative around secure and trustworthy and reliable AI for discovery, energy, and security. There's a nice acronym you can make with that. And the program that we're imagining is at large scale, and it has kind of these 4 main thrusts. So it has an integrated thrust at the top that's really about the science and math research needed to figure out how to do deep alignment of AI models with ethical response and responsible use. Think of this as enabling technology for making AI tightly coupled to human needs. The second layer is really a series of transformational hub scale centers. Hubs are things that are like 25 million a year, but we probably need something like 10 or more than of these, focused around these kind of 6 themes or new themes that kind of make sense, or hybrid themes, but that focus on major long-term challenges. These are not, 1-year things. These are 5, 10-year kinds of goals, and really align these large-scale AI pushes towards the program grand challenges across Office of Science, the energy programs, and national security. We want all of this AI infrastructure that we want to build, we need to build, to be built on a common cross-cutting platform, both on a software standpoint, workflow standpoint, frameworks, hardware, and so on. So that's this cross-cutting AI technologies. You could think of that as an AI kind of version of ST and ECP at some level. And then this has got to run on a very powerful infrastructure. So anybody who's doing large-scale AI research knows that if you look at the budgets at places like DeepMind or OpenAI, they're spending about 1/3 of their budget actually on computing. We, of course, have exascale machines, but the AI needs could actually consume all of our exascale machines and more. So we're going to have a program to build new, more efficient, energy efficient AI hardware and deploy it at scale and dedicate it to supporting the AI activity, so we don't steal cycles from the important simulation related work that we have to do. But we also want to integrate with the experimental facilities. So I think yesterday Ben Brown talked about the IRI. We see that as the essential ingredient to build a common infrastructure where AI can contribute to all the scientific domains and all the user communities that use DOE facilities. So we think of this bottom piece as dedicated computers and dedicated access, fractional access via APIs to all the facilities under a common software-based interface to tie everything together. So with that, I'm going to stop, and I'm happy to answer questions.
Thanks, Rick. Thought-provoking as you always are. So thank you for that. Questions, Roscoe?
Yeah, this is fascinating and interesting, and I can't tell whether it's the gateway to a giant new future or a hallucination. But I mean that and actually that was my question.
It's not a hallucination.
Whether this is a hallucination, but do you think for foundation models based on scientific data, the way you described, or do we know yet whether the issues around hallucinations and so on that we see in ChatGPT-4 are going to be different in some way, or will it be plagued in much the same way?
It's a good question, Roscoe. So, our group, I'm pivoting here from the broad group for a second, just talking about my own group for a second. We did this Gordon Bell Award project, using a transformer to design proteins last fall. And so we're in the middle of trying to understand this, right? Models hallucinate not because they have some goal, right, to hallucinate. They hallucinate because of how they're trained and how they're, and how you solve a prompt, right? So with the right training, with the right structures, and with the right downstream tuning, particularly things like reinforcement learning, human factors feedback, it's been shown that you can reduce the rate of hallucination substantially. Most of the current models are not, the data they're trained on are not highly curated. And so they have a lot of, weird stuff in the training data. And so at some level, what we have to understand is all of this, right? That's why this is a large program. I mean, ultimately, the idea of having a system that can be an assistant, sometimes, even people make up stuff. And so it's not going to be the case that models are always going to be, 100% truthful or 100% correct all the time. That's probably too high of a bar. But what we do have to have is a way of actually recognizing when something is made up. And those of you who are actually experimenting a lot, I encourage you to try out a system called Perplexity. Perplexity is a system that's built on top of GPT-4, but it uses augmented retrieval. And when you give a prompt to Perplexity, it actually goes out and verifies what the model is doing and comes back and gives you a mini report that actually has citations in it. And the rate of false declarations in something like Perplexity is very low. It's actually a startup that's being supported in part by folks working on OpenAI. There's also models like Claude that have been trained differently using constitutional AI techniques to try to be much more aligned with what a human is asking for. So I'm not really sure if I'm answering your question, but I mean, there's a lot of open R&D to be done here. There's no reason to believe that we can't solve this kind of a problem, but we certainly won't solve it by not working on it.
So I see a bunch of hands, so I'm just going to try to capture them in a roughly order that I saw them. So Sandy, you're next, then Sylvia, and then we'll do Gail, and Valerie and Christina. And Ed.
Thanks. Good day, Rick. I don't know what time zone you're in. You made a really good case on why DOE should be the lead, I'll say, for DOE, science, energy, and security. But you didn't talk much about interactions or partnerships with other U.S. agencies like National Science Foundation, who just stood up 7 centers, or about international partnerships. Satoshi's right next to me, like with Japan. Yep. Can you talk about that?
Yeah. So let's talk about international first. I think there's a significant opportunity for international partnership here. The national policy on AI, the national AI strategy, encourages strong partnerships with like-minded allies like Japan, certainly. And as Satoshi knows, we're actually talking about close collaborations around large language models and other infrastructure. So I think international collaboration will be a very important part of this. And we're identifying partners. I think there'll be partnerships. It's even one of the reasons I'm down here in Canberra. I think there'll be partnerships with Japan, with countries in Europe, with Australia, New Zealand, and so forth. I think international partnerships are super important. Interagency partnerships are also very important. I think NSF, of course, has a very broad mission and has been starting these NSF-style centers. And we think that the DOE approach would complement that greatly. It would create a scale-up mechanism and a way of engaging. There's also been discussion about how DOE might participate in the NAIR effort or the multi-agency effort. I also think that there will be a lot of discussions with other mission agencies about how the DOE direction that we're headed could involve partnerships with those agencies. And we've also been talking to NIST, we've been talking to FDA, we've been talking to NIH. So I think there will be significant international and significant agency partnerships, not unlike the Exascale program.
So I like to following up on the issue of partnerships about the data.
Who's talking?
Sylvia, sorry. So this is Sylvia.
Oh, okay.
So we need to make sure that we have access to the data, that, in the eventual case that we have a national security issue, we can have access to the data from many of the partners. It's just about the partnership, but it's about sharing data and figuring the way of doing it. And we
you have a question, Sylvia?
If that needs to be considered, as part of these partnerships, how to share the data between different organizations. But also, I would like to emphasize on the urgency of doing this. I agree with all the steps that you mentioned. I think that this needs to be done quickly. This is something that is evolving rapidly. When we did the workshops, we were talking about GPT-3 or 3.5. Now we have GPT-4, and there is a huge leap between the two. Yep. So I'm wondering what is going to happen in 1 year. So we need to move fast.
I agree with you. And there's been a huge amount of urgency inside the department. The 6 lab group that I mentioned that whose names are on the front of this, have made several trips up to the Hill, have briefed staffers in both sides. There's a huge amount of activity going on. One of the reasons that Jaron and I are learning how to get by with no sleep, put it that way. There's a lot of work going on behind the scenes to get this off the ground and to do it as fast as possible, because I think everybody understands the urgency.
All right, Gil.
Yeah, Rick, Gil Herrera. I must admit, I was a bit surprised by some of the language in the talk. Because given that this is for science, instead of seeing things like fairness and the kind of language that you need for privacy, which is very legitimate, I would have expected to see words like reliability, quantification of margins and uncertainty, and explainability. And
Sure.
so in the context of the scientific research, did you explore those three things?
Absolutely, Gil. A lot of that's in the report, and a lot of the uncertainty quantification and trustworthiness and reliability aspects were also discussed in the 2019 report. I think the language that's in this deck is probably, and we've had language like that in the deck that is probably edited to reflect more the conversation going on in the Hill. As I mentioned, this deck was, when we were working on deciding what to tell you guys, we decided to use the deck that we've been using on the Hill so you can see what the messaging is that's going on there. The underlying notion of how do we make strong AI for science where, we get out not just a prediction, but we get the error around the prediction is super important. And ASCAC is investing in that research now, and so is NNSA. So I feel like the version of this that would be a more technical dive into it would, of course, highlight that a lot. But we wanted you to understand the messaging that's being used on the Hill right now. And so that's why that wasn't in the talk.
I'm also sensitive to time, so just plea to be crisp. So Christina, you're next.
Rick, what I think the question is how we cannot be part of this AI wave for scientific advances. No, the 6 areas that you highlighted: AI for advanced property inference and inverse design, and all. Wow, they are very desirable for the U.S. competitiveness, for economic prosperity. So I think that's the question, and it will have to happen. It will happen with government leadership or without it, no? So what I think it needs always to be used is in combination with domain knowledge, no as a black box, but it has to be with a scientist in the room, which is perhaps what an idea of an assistant is the right idea. It's not the driver, it's an assistant, it's another tool. But how can we help here? What are you asking this committee to do?
I think we want you to be supportive of whatever is going to come out of this. I mean, there's been a lot of discussion about what's going to follow on to ECP. And some people have been arguing we just need to keep doing ECP, but that's not what's going to happen. What's going to happen is something like this. This has got momentum. It's a national imperative. AI is rolling forward. DOE needs to be part of that process. We need this for our own mission. And we also need it to be an independent broker. We need to have the same level of understanding and R&D so that we can become, as our historical role in many things in technology, a neutral broker around what's real, where things need to go. So we need your support. And this is not going to be a small initiative. This could be several times or more the scale of what we have been doing with ECP. And so this has got the potential of lifting computing at all the labs, and not just the computing people, but the domains, as you said, because we need to have the domain scientists full partners in all of this. So that's what we need, is support.
Valerie?
Thanks, Rick. This is Valerie. So it was actually a similar question to Christina, but really looking at the ASCAC community. So when you talked about, I think it's strides, if you could comment on what can the ASCAC community do to facilitate the push forward?
Well, I think the ASCAC, like many things, when we were working on building Exascale, we had a long conversation with Pat Damer, the leadership did, and she said, look, the most important thing to do is everybody get behind this and don't have internal squabbles, right? So this, in my mind, is the near-term biggest opportunity for our community. And we need to rally the troops around it so that as it starts making progress through the budget cycle and through the internal interagency process, that everybody hangs together behind it. I think that's the most important thing that we need to do right now.
All right, I'm just thinking about Jack has got a hard stop. He's going to have to leave. He's our next speaker, but I also don't want to cut off conversation too quickly. So Ed, you're next. Please brief, all of you.
Hey, Rick, it's Ed here.
Ed.
One thing I'm curious about is the application of this just to scientific literature. It was always one of my arguments, even back when I was at NSF, for open access. And if you just read the right 5 physics papers, you don't know which ones, you'd suddenly realize there's a new discovery kind of lying in the literature. And so these things seem to be exactly the right tool for this. And are you looking at that, and kind of what's the state of the art of that right now?
So we're definitely looking at that. I think the state of the art is that, as was mentioned earlier, I mean, these models attempt to do what they can do, but they're not good enough yet. So using a model as a theory assistant, as somebody who your trusted, super smart student who can read the literature 100 times faster than you and can keep pointing out what you need to be paying attention to, is what we're after. The models are getting there, but I think we're going to have to see things that are much more powerful and much more grounded than GPT-4 to do what you want and what I want. So that's one of the goals. It's one of the reasons why the way we frame some of the needs around the foundation models is around this notion of a hypothesis engine or a hypothesis generating assistant, because we view that as a huge opportunity. I mean, something that can read all the scientific literature and can make suggestions could be a game changer for many areas in science.
All right, in deference to our remote participants, I'm going to switch order a little bit. So Mark, Dean, you're next, and then Krista.
Hi, Rick. This is a good presentation.
Thank you.
One question I have, and I've been worried about this, is DOE working on anything, or is anybody working on anything that would keep an AI system from doing harm, I guess is the best way to put it. Rules to avoid, thou shalt not, do these things, is my question.
Yeah, so that's a very important question. This notion of alignment, whenever we use the code word alignment, you can think of this as something like Asimov's laws, right? And the trick is how to do that. There's several different techniques. There's guardrails where you kind of put boundaries around the side of it. There's this notion of constitutional AI-based training where you reinforce during training what is correct and what is good, and what is aligned versus what is not. So the model learns intrinsically to be aligned, but there's many techniques that are going to have to be developed. There's no single magic bullet for that. There's strong interest in doing that inside DOE, and it's a major element of the program. So that top layer that I described is in fact all about that. And it's not just about the soft part of it, it's about the hard part of it. What's the science and math behind making sure that these models in the future are aligned with human interests?
Do you think at some point, just to provide some coherence to the government rules for public safety, that the government will have to put in place some of these guardrails so people have to—
I think there will be regulation. I mean, the major AI companies are asking for regulation. They want guardrails as well, right? The issue is how to, even if you put it in place, you've then got to monitor, how do you catch bad actors? How do you even determine if a system is actually doing what you say it's doing? This is not easy to do. And one of the reasons why we think DOE can be a major player here is that, we don't have an axe to grind with respect to the companies. We have a mission, and we need this capability for our own mission. And as we understand how to build it for our mission, we can be helpful in that broader dialogue. I also think it's likely that DOE will have some kind of a role in monitoring in the same way that we do in cybersecurity, right? We're part of the National Cybersecurity and International Cybersecurity Network. And there will be, I think, something like that emerging in AI, where lots of eyeballs or AI eyeballs are looking at what's being done and try to identify whether there might be a rogue actor or a rogue system and how to deal with that. So there's many things that need to be done. And that's one of the reasons why this initiative, we're imagining it at the scale that it has to be, because this is not going to be small effort. It could affect everything that we do, both in research, but also everything that kind of affects the national mission in some sense.
Krista?
Yeah, thanks, Rick. This was a great summary and overview. I'd love to hear a little bit more on two items. One is the, viewing the AI model more as an accelerator to the HBC or ECP work. You mentioned making room for all the simulation jobs we want to continue to do. How do you see this accelerating those jobs or changing those workloads? And then second, how do we take a better advantage of all the domain expertise within the national labs in order to validate, refine, provide human feedback for these models? Is there a way you're thinking about that?
Yeah, so the first one, for this idea of AI surrogates, there's a bunch of projects happening already, and we imagine a lot more. The key concept there is learning these approximate kernels, right, that allow you to do an accelerated version of the application, but staying within the error, say, that you find acceptable for that application. And there's been multiple examples. I mean, in density functional theory, there's been at least a dozen or so papers where people have achieved more than 1,000, sometimes 10,000, 100,000x speed up. In our own work, we've built surrogate models for our drug response prediction case, where we've got speed ups of 50,000. And that enables us to fundamentally change what we can do. For example, with our surrogate model, I mean, I'm not trying to pitch my own stuff, but just an example, that's a case where we should be able to search over 1 billion molecules in something like 10 minutes using a surrogate model. So it completely changes what's possible. And I believe that concept is going to be hardwired into how everybody who's doing simulation thinks about their problems in the next 5 to 10 years, because it's just such a huge amplifier. It also could drive evolution of computer architectures and other things. So on that part, I think we have a handle. It's not a well-defined program yet, but a handle on how to do it. In terms of the domain people, look, we've got to build big teams. In the longer version of this talk, where I talk about how the broader AI community has come together to evaluate models and to provide feedback, there's this effort called the Big Bench effort, Beyond the Imitation Game, that have over 400 people participating in building test cases to test the AI and to evaluate the AI. We're going to have to do something like that in DOE, deep into all of our science domains. I expect it'll be over 1,000 people actually participating, not just for a workshop, but I mean, like, for years at a time to do this. This is like a once in a lifetime kind of transition in how we're going to do it, and we've got to figure out how to build the partnerships across all the domains. It's not just computer science and math. It's got to be with all the scientific domains as part of an integrated group.
All right, Satoshi, and then Tony, and we're going to need to wrap up.
Okay. Rick, yeah. Hope you're having fun in Australia. Having fun in DC. Yeah, so there are a lot of similar conversations happening at RICAN and also to some extent Japan with respect to AI for science. One thing that's noticeable is, and the question to you is, can DOE, do you think it's safe to say that DOE can assume leadership and how changing the mindsets of scientists in terms of how to collect very large amounts of data in a way they have not been doing before? Especially, like, part of RICAN is very much like DOE, but part of RICAN is very much, we have a whole bunch, like half of RICAN is biology.
Right.
And one of this deep discussion we've been having is, when you tell the biologists, we need more data to construct these foundational models, the interpretation of the word "more" to them is like factor 2. Right? No, they say, no, we need factor 100.
Right.
Yeah. In fact, a lot of scientists out there are not used to, unlike the big instrument type of experiments that DOE typically conducts. A lot of the science done out there, especially in biology, but also in other disciplines, is to basically they're throwing away most of the data effectively, but not gathering them systematically, continuously in high resolution, et cetera, et cetera, et cetera. And in fact, there are talks, that we really need to fundamentally change the way the scientists collect data.
I totally agree. I mean, those of you listening.
Really need to have the scientists think of innovative ways to collect data, especially in the multimodal settings, with new types of equipments, new types of parallelizing machines, just much the way that the genomic people have done by biology, but extending to like cellular sensing of cellular structures, et cetera. So you think DOE can play a role to innovate science in a way, not just by the use of AI for intelligent interpretation of these scientific data, but actually to fundamentally change the way the scientists collect data. And
I think we must do that, Satoshi. So I think in the spaces that are uniquely to DOE, I think it's maybe going to be a bit easier. But as you heard from Ben Brown yesterday, I mean, the concept of the IRI is essential to this, because if we get the integration of all the facilities with data and computing, it'll make it possible to do experimental runs where you gather more data. But there's also an interagency component. So I see Susan's raising her hand. You know, there's a strong partnership between DOE and NIH. DOE, of course, has been funding joint work with the National Cancer Institute, where we're actually working on this data problem. But I see interagency collaborations around changing how science data is collected and managed and published and opened up is very important. But there's going to be work even inside of DOE that has to be done, because we don't have a coherent way of handling data across the different program offices yet. So there's going to be both a social component, a technical component, and kind of an education component, right? If you show people scaling laws and AI and you say, look, here's a power law curve, and if we just keep increasing the amount of data, we know that our models can get good enough, and at some point there's emergence that happens, and not just in language components, but presumably in other aspects of scientific data as well. And so we need people to be willing to explore that and be okay with the idea that we're going to change the way we handle data.
All right, I'm going to give Tony the last word here, and Susan, I apologize, but we need to go on to the next agenda item. I'm sorry.
Rick, nice to hear your talk. Yes, so after the report we did in AI for Science in 2020, which had representation of across the whole of Office of Science, it was clear to me that the DOE had things to offer that was not possible in NSF, because Berkeley invented team science with the cyclotron and so on. But it was also clear that DOE did not have a major AI initiative as other agencies did, and it seemed to me that was urgent. So I welcome very much the engagement with NNSA, and I felt afterwards that was a missing element of the report, and we should have done that with engineering, energy, and security up front. The question I have, though, is the timescale, because I think this should have been done somewhat earlier, and we didn't. So the question is, with the cap and everything else, what is your most optimistic thing about getting any money to pursue such a program?
Well, it's hard to predict how fast Congress is going to be able to move with the budget agreement and so forth. I mean, the most optimistic scenario is some kind of a potential follow-on bill to the CHIPS Act that could happen, soon, this year, maybe next year. But I think, this is the most, in my view, it's the most urgent thing that we have to do. So I'm imagining that there will be some momentum created in the next fiscal year to do this. And of course, we also have the opportunity to remap a lot of the people that have been working on things like ECP and so on into this vector. I mean, at the scale that we need to pursue this, we're going to have to dramatically increase the number of people working in AI inside of DOE. And some of that's going to come from people remapping what they're doing, but some of it's got to come from new hires. But I think it's super urgent, as other people have said. And I'm hopeful that something could happen in the next, for fiscal 24, perhaps with some supplemental work on the Hill.
Thanks, Rick.
Thanks, Rick. We'll let you get some sleep. Appreciate this. I'll just echo what Rick just said. This is one of those opportunities, along with what Jack's going to talk about, that really suggests there is a tsunami happening in the future of computing, and we need to rethink some things pretty fundamentally, and it's going to require collaboration across a whole range of entities to make that happen. Thanks, Rick. Much appreciated. And Jack is going to now give us a report. Remember, we got a charge to look at the question about U.S. leadership in HPC, and the subcommittee's been laboring on that. Jack's going to give us the report.
Well, when I was asked to chair this this committee, Christine and Dan said this was going to be a report on international benchmarking. So I jumped at that opportunity to be part of an international benchmarking report. And then I realized that benchmarking is an overloaded term. So benchmarking did not appear in the charge letter. In fact, it was about competitiveness. So what we did is to write a report about international competitiveness. And so just as an outline where we're going here, we'll look at the charge, the team that put it together, an executive summary, findings, recommendations, and then hopefully some discussion. So this is the charge from Steve Binkley. I know you can't read it, but it says something like, how can the department maintain critical international cooperation in an increasingly competitive environment for both talent and resources? And I'm not going to read all the words. Identify key areas where the U.S. currently has or could aspire to leadership roles in advanced computing and high-end computational science and engineering, including worldwide capabilities. It goes on to ask about to preserve and foster U.S. leadership roles within reasonable resource constraints. Are there particular technical areas or capabilities that could be emphasized? And finally, how can programs and facilities be structured to attract and retain talented people? So that was the charge that we were given. The committee was really a committee made up of people from ASCAC, of course. Tony, Satoshi, and Vivek were part of the group. And then we had an all-star group of people who contributed as members of the committee. Greg Bell is at Corelight. He used to be at Lawrence Berkeley Lab. Eva Dillman is at ISI, University of Southern California. She was the vice chair for this report. Ian Foster, David Keyes from KAUST, Dieter Klausmüller from LRZ he runs the Supercomputing Center outside of Munich. Bob Lucas from ANSYS, a longtime friend. Lynn Parker was part of this committee. Lynn Parker is a colleague at the University of Tennessee. She took a leave of absence to go and work at the White House. She was the assistant director for AI at OSTP for a while, and then came back to University of Tennessee, where she's leading the AI efforts there. But she had a medical issue, so she had to excuse herself. John Shelf, Dan Stazione, Rick was involved in this project, and Kathy. So that was the all-star team that we had. In addition, we were provided support from people from the group here in terms of technical editing from Anne. Denise provided us with some logistics, and then my old friend Gail Piper from Argonne helped with some of the proofreading of the report itself. So the process that we used was, this committee was formed in July of last year, and we had a Zoom call in August to really form up and sort of split apart the call and try to identify things. So Tony led an effort to look at critical scientific areas in leadership, and Oscar, David Keyes took on advanced research tools. Eva was working with the building and maintaining strategies for industry and international partnerships. Vivek did the strategies for success, recruitment, and retention. So the idea was they would draft a component, they would be circulated, people would have a chance to comment. There would be another set of people who would take ownership of it for a while, and then it would come back to these guys for final review. So we had Zoom calls, we had an informal meeting at Supercomputing, we had more Zoom calls, and then we had a face-to-face meeting, which was, of course, very important to develop the report in its final form. And that took place in January here in DC. There were more Zoom calls to sort things out and multiple rounds of reporting and editing. We of course reviewed the relevant reports that had been generated and discussed with our colleagues in the DOE as well as at universities around the world. Okay, so here's the executive summary. The U.S. has long been an international leader in areas of advanced scientific computing research critical to DOE's Office of Science. And this includes the development of large-scale networks, computational facilities, and research in applied math and computer science. The ASCAC program has provided the necessary HPC and networking capabilities to support DOE's mission to advance the national economic and energy security of the U.S. And the products of this program are in use worldwide. So ASCAC can potentially maintain this leadership in critical areas while strengthening our research infrastructure and training the next group of scientists. Leadership requires significant increase in funding as well as innovative policies and programs. So we understand there's competing priorities, but and they have to be balanced, of course, but that should not limit our imagination and silence our advocacy for things. So we really need to keep pushing forward on these things. The ASCAC program is a key part of the U.S. Research infrastructure and has the responsibility to pursue its mission, including advanced scientific computing and advanced research facilities it requires with determination and enthusiasm. However, the U.S. Research leadership is at risk today. And with that being said, the research and technology tools that are the underpinnings of commerce, defense, environment, and society are at risk as well. The ASCAC program must not only develop and publish a clear vision with the associated list of goals, priorities, and recommendations, but it must enable scientific leadership by consistently securing this long-term funding. And this will allow the program to build on the achievements that have been realized to date and set forth an ambitious vision for the future. So that was the executive summary. And now for key findings and recommendations that we had. Some of these are similar to what Kathy talked about in the NNSA report. Some are motherhood and apple pie kind of things. So the first key finding, which is listed as a strength, is science and engineering applications of national importance will continue to require increasingly capable advanced computing systems. So, the national labs and the university partners are uniquely qualified to produce those advances, but only if supported appropriately in terms of leadership, vision, and predictability and sustained funding. The second one is also a strength, led in large part by the DOE. The U.S. is an international leader in applied math and computational science. It's also a leader in computer science, with DOE's role focused on those areas that are relevant to HPC, such as programming, parallel algorithms, performance optimization, as well as networking and data science methods and tools for scientific discovery. In part because of sustained, and that comes about in part because of sustained funding, collaborative research centers, interdisciplinary approaches, the HPC facilities, global collaboration that has taken place. Another strength is that HPC enables big data simulation and AI and machine learning, which are critical to scientific discovery and are synergistic. As we just heard from Rick, it's an important part of the overall portfolio going forward, and it needs to be addressed and funded appropriately. So HPC catalyzes scientific discovery by enabling efficient processing and analysis of big data, supporting high fidelity simulation and empowering AI and machine learning applications. Another strength is that the exascale computing effort is really an exemplar of U.S. leadership in high performance computing. It really incorporates the latest math and computational innovations into scientific applications, creating a comprehensive exascale software stack and advancing the capability of leadership class computing facilities to enable future breakthroughs. Cutting edge hardware software development has an impact on scientific discovery, economic competitiveness, national security, and global collaboration and overall influence. Another strength is that DOE has a history of partnering closely with industry and has a close collaboration there. So developing and deploying advanced technologies, particularly in the context of leading leadership class computing systems and cutting edge networking services. We heard yesterday from Christina Brown about the 3M activities that were going on. We heard also from Lori about the ECP activities that engages a wide range of industries in terms of input and leading things forward. It provides a mechanism for tech transfer, for shared facilities and expertise, for workforce development, for training, and for small business collaborations overall. So the recommendation now, so there were 4 recommendations that came out of the report. The first recommendation is on critical areas. So building on the existing strengths in computational science, advanced computing, and unique user facilities, ASCAC should be largely focused on these areas: high-end modeling and simulation for science and engineering. And that's for applied math, software, and advanced applications. It should also focus on artificial intelligence and for science and engineering, as Rick has articulated in the previous talk. We should be looking at leading edge computing architectures and systems on a path towards post-exascale computing, looking at hardware architectures, software, and deploying those architectures. And we should be looking at advanced networking and future internet architectures for integrated research infrastructure. Again, looking at architecture, software, and deploying those infrastructures. So each of these areas has a long-term research challenges that should be pursued through a combination of base funding that is promoting career development within the Department of Energy, and also opportunistic calls that provide the flexibility to address things. So we're pretty strong on looking at base funding being reinstated within the ASCAC program, as well as the normal opportunistic calls. Each of these areas also demand the development and deployment of infrastructure, such as codes, libraries, AI, data at the edge, and that all go into supporting a broader user enterprise. Another key finding, which we felt was a strength and a challenge, was the end of exascale computing program. It was a huge success, I have to say, and it's one of the, I've been involved with DOE for the past 50 years. I started when I was an undergraduate at the Argonne National Laboratory, and this is one of the most rewarding projects, I have to say, that I've been engaged in. The project delivered really great capabilities, both in terms both human and technical achievements. The DOE, of course, is highly vulnerable to lose the knowledge and skill of that trained staff as future funding is unclear. So basically, we spun up this cadre of people who can work with exascale computing, getting them engaged in applications, software, and the use of these machines. And the spigot is about to be turned off in terms of funding them. And now we have the unfortunate situation of perhaps losing those very talented people who can't be easily replaced in a program. So there needs to be, there really is this major source of uncertainty. When we talk to people at the labs, there's great anxiety over the end of ECP, and no clear message has been communicated about what the post-ECP plans are. We heard Rick talk today about AI, but that may take a year or two in order to get the funding in place and engage that as a full-grown program. there's a need to be a sustained program to look beyond exascale. And I have to say, when we have our annual meeting, getting the group together, getting a group the size of 300 or 400 people in the room discussing applications, hardware, and software is really a invigorating, energizing situation. So it really was a great program. There are many challenges here for OSCAR, the DOE, and the U.S. in general, in terms of leadership in critical areas. So global competitiveness, there's competitiveness from China and Japan and several other European nations that are really heavily invested in scientific research. I know you can't really read that graph that's there, but that's trying to give a glimpse of how much investment there is in research as a percent of the R&D as a percent of the gross domestic product of the countries. And the blue line there is the US. So if we're taking a look at this thing here, this blue line here is the US, which is increasing a little bit, but not great. This is the red line is China. And most of these are European countries which exceed the US in terms of GDP spending on research. So we understand there are funding and budgetary constraints, but there needs to be a clear strategy to grow funding for sustained leadership in these critical areas. As Rick pointed out, that's going to be a process, and we hope to engage in that. Looking at even the top 500 list, what we see in the top 500 list in terms of U.S. Dominance. U.S. at one point had great numbers of machines on the top 500 list, but recently China has surpassed the U.S. in terms of its numbers. And then there's this brain drain and talent issue, trying to retain top scientists who can continue the program. Even within my group in Tennessee, I see people in my group being snared away to work at places like NVIDIA and AMD, places where they can work at home, stay in Knoxville, and earn much higher salaries. And they're offered things that I can't offer them, like stock options. So, there's great incentive there for them to perhaps move on from where they are. So another challenge is the technology landscape has changed. The DOE and OSCAR must embrace this agile and innovative and strategic visions. We have Dennard scaling ending, Moore's law is waning, hyperscalers are on the rise. So we see custom silicon being created. We see many other disruptive technologies. We talk a little bit about quantum in the report itself. By adapting by adapting to these emerging technologies, we hope to foster interdisciplinary collaborations, forging strong partnerships going forward, and engaging with global counterparts. And another challenge is, unlike the past, today's scientific and research landscape and HPC supply chain is really a horizontal and international. We can't rely on acquiring all of the components here in the US. We have to rely on other places for them. Leadership in HPC requires proactive and long-term and sustained engagement with this broader international community. Industrial partners are essential and merit attention and improvement. And this notion of co-design is really going to be key moving forward in terms of high performance computing. All of these things help develop standards and interoperability that we can help by recruiting from a worldwide talent pool. Open science and open source, of course, are the key phrases there, and collaborating perhaps on funding models as we go forward. Taking a look at the budget for OSCAR, we have the following situation. I call this, the research is level or declining in terms of real terms. So this is the OSCAR budget going back to 2013. Blue is the research component and green is the facilities. When we started in 2013 here, the research budget was about 43% of the overall OSCAR budget. And today the research budget is on the order of 34% of the overall budget. So it's a shrinking with respect to the total, where the facilities budgets are up and to the right. Over the past few years, the research budget has remained more or less flat going across. There's a component there in light blue, which is ECP's component to the research budget. And of course, that's going to go to zero at the end of this calendar year. So that's an issue that's going to happen. And we don't really know what the story is going to be going beyond this point in 2024. So that raises some, I would say, challenges in terms of the leveling or declining in real terms of the research budget itself. Another challenge is, the attractiveness and prestige of a career at national labs has been on the decline. It was really the foremost place to work when I was, at least that was my feeling when I was growing up. And today we have increased competition from many sectors. Lack of long-term programming vision and stable funding is in part to blame for that. The funding uncertainties at the end of ECP is causing that cliff regarding confidence and the ability to retain and recruit talent. Again, the people that may leave the program because of the funding issues, they're not going to be easy to replace. And it's going to take a while to spin up the next generation of people if we do have a great departure from our people. Funding challenges have impacted the attractiveness of the careers in the national labs. In an era where we have budget constraints, the national labs have faced reduced funding and tightening of the budgets. And we understand that bureaucracy is another issue that perhaps prevents joint appointments from coming about. I can speak from my own experience. I have a joint appointment with Oak Ridge and Oak Ridge National Lab and the University of Tennessee. And almost every year I'm called on the carpet by one of the groups, the university or the lab, and it's trying to explain to them how my intellectual property is going to be shared somehow between these two organizations. It's sort of a thing which gets in the way and just really is a distraction from the overall thing. So we need to work out some way where we can, in fact, get around some of that and have joint appointments. So here's the second recommendation for vision and planning. Oscar leadership should work with the DOE labs to develop a decadal plus post-exascale vision and strategy that builds on the strengths in the mathematics and computer science and computing research program, working together with world-class facilities. The focus should be on providing sustained investment to preserve and extend Oscar's current leadership in computational science research and multidisciplinary teams, while also establishing new application areas in emerging topics. And we've heard about some of these emerging topics, AI for science, energy, and security, of course, being the one at the top. Maybe digital twins is there, and also post-more technologies are to be considered. Another key finding, sort of an outlook, is big science and advanced scientific computing increasingly requires international collaboration. International collaboration facilitates exchange of knowledge, skills, and best practices. It enhances our global impact and relevance of scientific computing. The collaboration fosters data sharing and access to software, as well as large data sets, and it provides significant opportunities for collaboration existing in areas such as standard interfaces and libraries and much more. Things like MPI could not have happened without international input and collaboration to get that rolling. Without that help, I think it would not have been quite the success it was. So another recommendation here is about vision and planning. Oscar needs to articulate a vision and the associated goals and milestones for international collaboration focused on post-exascale computing. Oscar, in partnership with the NNSA and other scientific computing and energy offices, should strive to become international leaders in AI for science. So that's the future. As Rick has pointed out, research in AI for science and energy and security problems the software stack that'll be used to move that forward is sort of critical for that. So ASCAC should work to establish trusted relationships with strategic partners, evangelize and socialize those efforts, defined agreements, structures, perhaps a memo of understanding, as well as provide resources to develop flexible multi-partner collaborations. Looking at another key finding, this is viewed as looking forward. ASCAC facilities will continue to require interdisciplinary approach, requiring co-design rather than relying solely on the vendor marketplace. This is an issue that really is at the front today, with only one vendor really supplying high performance computing resources to us, one or two. This approach fosters innovation by looking at co-design and scientific knowledge, and the culture of collaboration is there. So the current approach to designing HP systems really must change. We talk about co-design, but it's just some words on paper. I can't point to many areas where co-design was used to develop the exascale machines. The model that I have is that we set out a price tag. We said we have to have this level of performance, and the vendor then throws a machine over the fence, and we are going to scramble for the next few years trying to figure out effectively how we can do that. And we really need to embrace this end-to-end co-design, perhaps through custom hardware, configuration and packaging. We have the ability to do some of that today with using chiplets. You can see what's happened in terms of high performance computing. This is a graph of the top 500 list over the years, and we're looking at from when the list was first done when was that? So that was about 30 years ago, and we're looking at the 500 machines. And in this particular graph here, we're looking at the machines that have the x86 architecture. So architecture that's built on top of Intel and AMD chips. So for the most part, 97% of the machines today that we have on the top 500 list are built out of those chips. Some of them use accelerators, but that really is a strangle point in some sense for our architectures that we have today. And we'd like to go beyond that. And if we take a look at the hyperscalers, they're designing their own processors. They're designing their processors. Alibaba has a processor that they designed to help them. Amazon has their own Gravitons. Google, of course, with their TPUs, and Microsoft has their set. So perhaps we should, in the Department of Energy, engage in a program of looking at custom hardware that we can really use to co-design a system, and do that such that we design prototypes at scale so we can test out ideas. There used to be a rich history, I'll say, of looking at architectures at universities and designing machines and building things. And today we've lost some of that. And I think we need to recover some of that going forward in terms of high performance computing. So another recommendation here, a strategy is ASCAC needs to invest in long-term forward-looking co-design research in advanced computer architecture, hardware, and system concepts to identify potential solutions for sustaining continued scientific productivity increases in future scientific computing systems. Such a co-design effort would require a substantial increase in government investment in basic research and development, and DOE should fund the building of real hardware and software prototypes at some scale to test out these new ideas. So it's not going to be business as usual. That was a message that Kathy had in her talk about the NNSA going forward, and it's going to be echoed here in this report as well. Okay, so here's the conclusions. DOE, ASCAC, and the labs are in this existential crisis. The U.S. is losing its historic leadership position in advanced scientific computing research. The trend will likely lead to the U.S. producing a smaller overall share of the technology innovations. A major factor contributing to this decline is the significant investment in funding research by other countries and reduced investment in the intellectual underpinnings, raising concerns about future success of DOE's endeavors. The U.S. was long considered a desirable destination for a career development for scientists and its national laboratories with respect and was respected worldwide as hosting the most talented researchers. And this is no longer the case. Funding uncertainties and the move away from sustained funding intended to produce foundational innovation to short-term research contracts focused on near-term goals has made the Department of Energy laboratories a far less attractive location for both junior and established researchers. And finally, OSCAR should revive this notion of stable funding, maintain its stewardship in state-of-the-art facilities, and develop a long-term visionary research program for advanced scientific computing. There you have it. That's my story, and we're going to stick to it.
All right, before we all go commit joint ritual suicide here, I mean, these are serious issues, and this is why I said in my opening remarks there are common themes that run across all of these issues. That business as usual is not going to get us where we need to go, and $1 million here, $1 million there. Not that it won't make an incremental difference, but these are multi-billion-dollar questions we're talking about. And we're talking about the future of U.S. leadership in a whole variety of STEM-related technologies and workforce issues. So it really is important. And now I'm opining, and I'll throw it open for discussion. How we as a country articulate and drive closure to an implementation of a strategy that will secure the future. And so with that, questions, Ed.
Thanks, Dan. And Jack, thanks. I really liked not just the results of the study, but the tone of it. I mean, it's not hysterical, but it's grave. You know what I mean? So it's very, very hard-nosed look at everything. So it's really good. I'm just really curious about your thoughts on the NSF. So it used to play a much more important role in this overall effort. I didn't show up anywhere in your slides in terms of like a collaborating organization. And I just wonder if you see its sort of lack of attention on these topics, I mean, at the level that's needed as a part of the threat, or if, any thoughts on that generally?
Right. So it didn't appear explicitly, but there was collaboration cited in the report itself, where easily it fits. NSF requires high performance computing, not quite at the level of the Department of Energy. NSF is engaged in research, but not the kind of research in general, not the kind of research that is applied research that can easily fit into applications and driving them forward with practical results going on something that could easily dovetail into an active program. So I see NSF providing some of the long-term historic computational underpinnings that could be used within that. Occasionally, NSF does provide things which will be most useful to DOE. So there is grounds there for collaboration. But I would say that in terms of computing resources, the Department of Energy is the one that has the need for the large computational resources overall.
All right, Valerie, then Karen, and then Satoshi.
Oh, so yes, I know. Thank you, because I forget to turn it on. So thank you. So thank you, Jack. I really enjoyed the presentation and the report. It's very comprehensive in its findings and also recommendations. So I applaud the committee. I just wanted to note a few things too, and that is especially with the long-term funding that is so important for innovation, because having that sustained funding allows opportunities to try different pathways before getting to the right pathway. So, I applaud the focus on the long-term funding. I also wanted to bring up too, when we look at the staff at our labs and competing with industry, we're also competing with academia as well because of the 9-month salary that give that stability. So I think noting the importance of the stability of funding is important. And that's where academia, currently, we're losing staff a lot to academia because of the stability of the 9-month funding. That becomes an important aspect. And I think especially with ECP ending, that academia is there recruiting heavily. And then I also wanted to applaud about the co-design, especially I think what's taking place now in the microelectronics. So I noted that in the report too, that it was noted about the microelectronics as an important aspect with co-design across the full stack. So I just wanted to, I don't have a question, but I just wanted to applaud the committee on the findings and recommendations and note some particular aspects.
Thanks, Valerie. Yeah, so I guess we don't have the luxury of having tenure in the DOE system. So that's one of the issues. And as you point out, university professors, they have a day job that they do, and then they can go off and do their research and have also the summers to engage in more active research.
Right. And in some universities, while it's a 9-month salary, is over 12 months. So that summer, while you can get grants for the research, you also have that time to work on the research.
Yep.
Yeah.
I just want to add my applaud and of the fantastic work and on this report. So I guess a couple of questions. I wonder if we can be a little bit more quantitative in the numbers. The first is related to the ECP, and we completely understand and have heard, the alarms, right, of the staff and the scientists and engineers. But I guess, do you have a sense of the numbers? How many sort of a little bit, or maybe it's not possible to really get that number. What is the number of people that we are expected to lose? Or it seems to me like we're going to face this gap. There's nothing that's going to happen, I see, in the next 6 months that's going to close this gap, unfortunately. So that's my first question. I have a
So
second
let's see.
one, but yeah.
I'm going to turn it over to Lori because I know she has the real answer. But my impression is there's 1,000 people who are funded out of working on ECP. Maybe half of those are in the Office of Science, but I don't have the exact number. Lori?
So is this on? I can't tell.
Not yet.
Seems like it's on.
Oh. Go ahead. Too late.
Yeah, so we have been tracking this pretty regularly, and at this point, ECP touches about a little over 800 people. That does not include subcontracts to the universities, so that's what we touch at the labs. And then it's about 400 FTEs, again, at the labs, doesn't include the subcontracts to the universities, but we have been very carefully tracking that and looking at trends over time.
Thank you. I guess maybe a suggestion, I don't know if it's appropriate or not, is to include some of those numbers in the report because it makes it more real. That's a large number of people.
Yeah.
Obviously we're probably not going to lose all of them, but there's probably going to be some fraction of those people that we will lose. And having heard, Rick's presentation just before, how do we start this new initiative, with this leaking faucet of people that we're losing on the back end. So that's one comment. The second one is also quantitative with regards to, I completely agree with having long-term funding. That is just, it's also something, despite the fact that I'm in academia, and yes, we do have a 9-month salary, and that's kind of a good thing, but you can't do anything with a 9-month salary other than teach and buy a few pencils and paper. So you need research funding. And the problem with the research funding is that it's not long-term. That's really fundamental. So very often not even long-term enough to guarantee that a PhD student is going to finish, right? Who gets funding for 6 years? Nobody. It's usually 18 months at a time or 12 months at a time. So I totally get that. So I think for the labs, it would also be good to get for people from outside the labs, right, to understand what's the scale that we're talking about. We were just chatting, doing something like co-design and anything that you touch with hardware, the number of digits goes up very, very quickly, for spinning out chips and things like that. So I think it would be adding more quantitative numbers to this report. Again, I don't know if it's appropriate or not, would be more impactful in my suggestion.
Okay, yeah, I get your point.
There is a Hobson's choice, I will point out, which I don't know that we want to make, which is you could divert facilities money to support people. That is its own set of implications. But I agree that in 6 months, there's not going to be any new money. That's the hard choice. All right, Teresa has been waiting patiently online. I'm going to go to her and then I'll go to Satoshi and then I'll follow up with the rest of you. So Teresa, go ahead.
And so I just wanted to add that I really appreciate the balance of the report as well. I think the other piece that I really appreciate is that we have built up this great strength in high fidelity physics-based models, and the support from the ASCAC applied mathematics and the computer science has been essential in that. And so not losing that capability is really important. So I just really want to applaud that. And I guess I also want to, maybe I'm on the 5th person now saying that this long-term funding idea is really, I think, very important. ECP was essential for us to be able to explore different things that we would not have explored otherwise, right? Because we just would not have had the time in a short-term funding. So those were just my comments.
Okay, thanks, Teresa.
Satoshi?
Yeah, so this is something we've discussed last night, but so I sense, and this is a realization I've gained during this meeting, so this could be something of proof of thought, maybe to add to the report. So in the old days, there were machines that were thrown over the fence, and then the labs, and it was the same everywhere. It was the same in Japan too. People basically work hard to try to adapt their codes or whatever, or have new methods or whatever. So there was this, and that was one of the reasons why I think the basic research funding was more abundant. Right, research funding more abundant as opposed to just facilities. The facility guys did their job out of sync with the research to some extent. Then exascale era was foreseen, and this model was changed to be much more orchestrated, and thus the incorporation of notion of co-design. That there will be more cohesive process by which the applications and the machine development would happen in concert. And as such, you would be developing the co-design efforts really, for example, we did exactly the same for Fugaku, in that we had the co-design from the application perspective was in part working with the machine people, the system people to kind of do an iterative design. But the other was to, in fact, the bigger portion was the application readiness program, to make sure that the applications would be ready when the exascale machine arrives. Because now there's a realization that you can no longer throw things over the fence, but rather there needs to be more concerted effort to make sure that the sciences that will be enabled by these machines will be there as soon as the machine arrives. So this is a new model. It's not business as usual. In fact, this is already a new model.
Yeah.
So what you were really supposed to do in that case is to make sure that when the machine arrives, there'll be sustained investment in the application space. So in our case, what we did at Fugaku was to, as soon as the co-design, what's called a 9 important areas. But was over, there was continuum in which the projects that were involved in the co-design got continuously funded. Of course, there was some screw up with the ministry where the funding value was reduced and all that. But largely the money, the money for the application teams, as well as the 40% of the K computer was used for the co-design, and that was carried over to Fugaku, so that there was a 40% of the entire Fugaku's resource committed to the application teams that had been involved in the readiness program. So, and the other general allocation happened outside of that 40%. Right? So it was 60%, well, about 40%. Well, I won't go into the details, but there are some percentage that's for general allocation, but 40% is exclusively reserved for people for the applications that were enabled by this exascale in our exascale program. So then, and I was shocked to find out that none of this happened for ECP, right? Because Laurie's presentation yesterday said, "Oh, this will continue, but what happened? Well, if this is over, what would happen to the application teams? Is there a commitment of funding? Is there a commitment of resources? There doesn't seem to be, which I find to be quite, this business as usual was supposed to be made into a more strategic one, but wasn't followed through. And as such, not only the assistant people are left in the dark, but also the application teams now have to compete from day one to get the resources. And so I think that's not a very good strategy. And additionally, what I fear is, and there are suggestions for investments like AI and things like microelectronics and all that. But if this is all to enable application science, I didn't really see the clear plan with respect to how to make this into a strategic program, thereby enabling applications even after whatever machines are constructed, right? It's because, we're not, on one hand, we like to explore to research on the system side too, but we also are responsible for building an infrastructure. And when we build an infrastructure, there ought to be programs for the application teams to have committed to conjoin to build this infrastructure together, to have sustained funding so they can use the infrastructure, right? And that's totally missing.
Thanks, Satoshi. I don't know if there was a question there, but thank you for those comments. I know you helped write the report.
So we need to decide on a vote on this, but there are 3 people left, and then I want to bring things to closure. So Martin, and then Rick, and then Christina, and then we decide on a vote.
We have a lot of anecdotal evidence about the short-term funding and competition and so on. I wonder why there isn't some kind of workforce survey or use of exit information to actually really put this on a more solid footing. I mean, all of us have seen this in the labs. We've seen people who are uneasy and unsure about their futures and want to do something about it. And then I look at the different ways in which different parts of DOE is funded, from headquarters where they have pretty safe funding, to the facilities where they have more fund, sort of more secure funding, to the people who have to scurry for, 5 or 6 proposals a year to stay funded. And I wonder what would happen if everybody had to write 5 or 6 proposals a year to stay funded. I think the system might change awfully fast, actually. And so I see something of a disconnect there in terms of the different groups. And I suppose the idea is these short-term funding and multiple proposals keeps you sharp and keeps you active and everything else. I think in reality, it just tires you out. And so I think it's a dated notion. And I think it goes back to some idea about competitiveness that's rooted in, maybe the philosophy of 20 years ago, and doesn't really fit with the modern world of work and the competition that exists both in academia and in the tech sector. And so I think there has to be a long, hard look at the realities of what's going on here and how you keep people. Without DOE's workforce, it's nothing. End of story.
Yeah, it's all about the people.
It's all about the people.
Yeah.
So I would like to suggest it's even bigger than what is scoped here. The industrial labs have also declined in their ability to do fundamental research, focusing more on short-term objectives and having to chase funding on an annual basis, with possibly the exception of the financial sector, biotech, and then social media and ad delivery. There are other countries with programs like Fraunhofer and STFC that have national resources that are available for the more fundamental research for industry. And as we see the Xerox parks and Bell Labs and now the splintering of GE research and such affecting the economic competitiveness, and maybe 3M is in the same boat, it's even more reason to have a resource like the DOE labs that are capable of doing this.
I couldn't agree more.
Yeah, I agree with you, Rick. But my part was about how, maybe the report, I didn't read it. I don't know if I got it. Oh, it says that it's on, but not up here.
That's better.
Okay, is it wrong?
It's on. You're on. You're good.
Okay. How about highlighting, and I like what Karen said, because data matters. With data, with numbers, the projects, the applications, the scientific outcome that is going to stop because of the easy funding. You know, my life, the argument of talent has its weights, but it's limited. It's much more important to tell leadership what they are not going to have because of the decisions of stopping the funding. What are the real clear things that are mission critical that we need to deliver as leaders, and it's not going to happen. So I think a little bit on the people. I like that, and the people is what drives everything. In industry, it's also the talent. But at moments of these arguments, it's also what is not going to happen because I'm going to care that that's not going to happen anymore. I'm frankly short-sighted to make such an investment and only reap certain benefits during the period and not continue to return of investments on the capabilities that were built. That to me is sad, and it doesn't make sense.
Roscoe?
All right, Roscoe, you really get the last word, and then we have to vote.
So I just wanted to say we told you so. In the 2020 report for that ASCAC accepted about the future of ECP, we had a third of that report was about the impact on the workforce and the impact on the country. And the reason I didn't want to jump up and literally say I told you so, but I am. And I think all that goes to is that I'm not sure that this information is going to the right people, because it's the people who control appropriations and the national picture who need to hear it. And I'm not sure our report ever went there. I never saw anybody in DOE that we reported to directly who said, oh, you're wrong. UCP, doesn't need to continue to have those people supported and doesn't need to continue the work. So in part, that's why I was trying to ask yesterday, how can we get that message out most effectively? But anyway.
I mean, look, here's the budget reality. With the budget caps in place, we're talking about potentially 1% increases. With inflation running what it is, that's a de facto budget cut. The only viable strategy is one that a version of what Rick articulated. It will require emergency appropriations outside the regular order in order to support these. Those then have issues about sustainability as well. You'd have to get them folded into the base budget. But the story, in my judgment, is it's beyond a program or beyond an agency. This is about really the future of U.S. global leadership in computing writ large, because as Kathy talked about yesterday, and as Jack just did too, and Rick, all of these issues are connected. Next generation architectures, algorithms, software, people, they're all part of 21st century, who's going to own the future and information technology question. And frankly, the two politics that I've seen get traction in DC are China and competitiveness and domestic workforce issues. You know, so if there are ways to tell stories that can leverage those, that I think is what we have to do. And I'll end my soapbox comment there. But Jack's eyeing his watch because he's got to catch a plane. So here's the practical question. Karen raised an important issue about whether one could add some quantitative data about the ECP workforce. If it's possible to do that, I think that would be a good idea. The question before us is, are we prepared to vote to accept this report?
That's addition, yes.
Okay, yeah. So if we make that everyone okay, then I'll ask just for all those in favor of approving, say aye.
Aye.
Any opposed? Extensions? All right, great. Jack, thanks to you and all of the members of ASCAC and more broadly, the members of the committee for putting this together. It's an important message. And sadly, I fear Roscoe is right. We told you so, and now we're seeing the consequences. On that sad note, let's move on to something more positive. Let's talk about early science on Frontier.
And Bronson, if you're there, if you can compress your talk a little bit.
I will try my very best. I know I'm not between you and lunch, but I am between folks and other things. Can everybody hear me okay?
Yes.
Terrific. Okay, and I will try to be a little more optimistic in my outlook. I think we have reasons to be, so I think that's a really good thing. I am compelled, for folks who don't know me, I'm Bronson Messer. I'm the Director of Science for the Oak Ridge Leadership Computing Facility at Oak Ridge National Lab. And I'm here to tell you a little bit about the early science that's starting to be produced on Frontier in Indiana. I'm sort of compelled, I often say by law, to tell people what the mission of the leadership computing facilities are. And it really is to provide resources to enable scientific inquiry that cannot be done anywhere else. And I think that's an important consideration in the kind of science that we undertake, the kind of science we deliver. And it sort of guides in many ways everything we do, including the way we do it. I think Satoshi earlier talked about application readiness. We do take that very seriously, and I'll get to that in just a second. I think you also heard earlier in the meeting that Frontier is open to early production, all allocation programs. So Insight, our ECP allocation program, ALCC for the last allocation year, a very small set of allocations were enabled, and all of our directors' discretionary projects have been enabled on Frontier since about the 1st of April. That's almost 1,300 users and almost 170 different projects. And we've delivered more than 10 million hours. This is an update from maybe a number you saw earlier because I went and checked it this morning. Have been delivered to these programs to date in 2023. Where did these cycles come from? Where are they sort of brought forth from? Well, we have instantiated an application readiness program we call CAR, Center for Accelerated Application Readiness, every time we've built a computer since we built Titan at the beginning of the last decade. And it was because we had this realization that we needed to do something to ensure that scientists would be able to take full advantage of the architectures that we were fielding. We built the one for Frontier based on experiences and a lot of lessons learned from CAR programs for Titan and from Summit. And the tactics that we use to sort of do this is we have direct in-depth collaboration with OLCF staff. We pull in our Center of Excellence vendor partners, other computer scientists and applied mathematicians from not only our center, from around the laboratory. We typically hire a postdoc for each one of these projects as well. And we try to make sure that their tenure overlaps both code development and delivering science with that code on the machine that we're sort of aiming at. And of course, we do provide allocations to compute resources. During development, there was a lot of allocations on Summit, early access systems. We're also committed through various channels, our DD program, Insight, and ALCC, to making sure that each one of these CAR programs, and indeed the ECP AD projects, which are also very much like the CAR projects in a lot of ways, have ample resources to ensure that they can get the job done. This is a list of the car applications for Frontier. You can see that they sort of span the full, maybe not the full gamut, but they're not a bad basis set for the kind and variety of science that we do at OLCF. They are, I think, distinguished by their diversity and depth, and sort of I could slice these applications in 1,000 different ways, from programming models to, frankly, the culture of the scientists and engineers who mostly do the investigations in those fields. Just to give you some examples from CAR of what we've been able to do, LSMS is sort of a repeat offender in our application readiness program. It's a large-scale DFT code. It's been used to study, for the most part, materials where talking about the regular crystalline lattice just doesn't cut it anymore, where defects and small differences in the structure of the material is actually where the action is. It's where most of the phenomena that are important to these materials actually happens. This notion of disorder and defects in materials and how it affects their electronic and mechanical properties, that's the central question for LSMS. And because of that, they basically have to do DFT on a lot of atoms. Well, it turns out that once you make a code very, very capable on an exascale platform, in DFT, you have to do the same sort of thing you have to do in molecular dynamics. That is, if when you start a calculation, you need to establish who your neighbors are. You need to build a neighbor list for every single atom that's in the configuration. And it's probably not an everyday occurrence, but sort of million atom MD simulations are something that get done fairly regularly on major chunks of big computers nowadays. It turns out that if you build neighbor lists very naively for 1 million atoms, it can take you an hour and a half, even on a very fast computer, to build that neighbor list. The good news is, if you're one of the LSMS developers, you can go down the hall to some of your colleagues that actually are MD practitioners, and they can give you a much better routine to be able to build that neighbor list and cut that time from an hour and a half to a handful of minutes, for example, to do a million atom neighbor list. And because of that, LSMS was able to scale up to almost essentially the full size of Frontier for this 1 million atom iron platinum system that really does show this sort of inhomogeneity and difference, and sort of is freed from the tyranny, if you will, of periodic boundary conditions. COMET is another sort of repeat offender in our program. COMET is used to compute similarity metrics, and especially for genome-wide association studies for things in genomics. So it looks for pleiotropy and epistasis. So pleiotropy is a gene that doesn't just control one phenotypic trait, may control many. And epistasis is individual alleles sort of interfering with one another or feeding back on one another and expressing new sets of traits. You might expect that that was an important consideration when looking at the evolution of COVID-19 variants across the globe, both in space and in time. And indeed, that's one of the first problems that was attempted with COMET. And it achieved the 6.71 exaflops, where exaflops is mixed precision exaflops. But with a completely off-label use of the reduced precision units on the machine. That pleiotropy and epistasis that I just talked about, I don't think it's very hard to convince yourself that when you write down sort of a correlation between those kind of things, what you end up with is a problem in linear algebra. And it turns out that you can use the reduced precision units to give you a very good preconditioning step for the kind of systems that you achieve in these GWAS measurements. And that's exactly what this code does. It uses those reduced precision units to do really smart preconditioning for those systems, and does it a lot. And therefore, the total amount of work that gets done in a period of time is very, very high. Again, we have an interesting relationship, a very synergistic and complete relationship with ECP projects, especially AD projects, because we're sort of used to doing the sort of things that ECP AD has funded over the past few years. We made the decision a while back to select 12 AD projects to sort of give special attention to, because we thought we had a really powerful lever arm to be able to influence them. And we basically just brought them under the CAR umbrella. And this is the list of those applications. But other ECP applications have also made a very effective early use of Frontier and have really shown some interesting returns. Maybe chief among those, of course, was last year's Gordon Bell winner using WarpX. I have to say that the Gordon Bell Prize is something that I'm often ambivalent about, right? It's always nice to see good performance on real code, but sometimes the calculations are contrived, let's say, to make sure that you highlight that. This is an actually very unique notion about using laser wake field acceleration on a solid target to increase the number of electrons that you get in each bunch. You need to build a system where you're going to hit a gas typically with a laser, evacuate portion of that gas of all the electrons, and then the electrons sort of surf behind these bubbles that you form. Well, if you try to do that really, really fast, you actually can't build up enough electrons to give you enough charge to do a certain task. Maybe a good way to do that is to throw the laser at a solid target where there's a lot of electrons, immediately ionize and rip them apart, form a plasma mirror and let that reflect into the gas that you're going to use to build this laser wake field accelerator. And that's exactly what this simulation did. I think this is an exciting notion, and it's already being tested in the laboratory as well. But the ability to do this quantitatively, to be able to basically count the number of electrons that you get in each bunch and determine whether or not that's going to be adequate, for example, for things like fast radiotherapy, is really a hallmark of exascale calculation. Another ECP team that's made a really effective early use of the machine is Exalt. Mostly, it's primarily an MD situation, but the particular problem that they looked at was the damage to tungsten surfaces relative in plasma-facing materials and fusion reactors. It uses a handful of innovative things, the SNAP potential, which is a machine learning-based materials model. It also uses this sublattice parallel trajectory splicing, or parsplice notion, to accelerate molecular dynamics by trying to parallelize the time dimension. So, one of the problems, if you will, of molecular dynamics is all these darn semi-stable states that don't represent global minima, but are local minima, and sort of trying to kick configurations from one to another. It's a common thing, for example, to do something called replica exchange, where you put configurations in certain configurations and have them at separate temperatures, and then sort of let them swap temperatures to try to kick you out of these local minima, these local basins that serve as attractors. With parsplice, you actually keep a lot of that information, and you carefully splice a transition from one of these metastable states to another to be able to get a final trajectory that's sort of parallel in time. But you do a lot of different trajectories. I liken it to the bit in the Avengers movies when Doctor Strange sees all 14 million or 14, something like 14 million possible visions of the future. That's kind of the way parsplice works. But it takes an exascale computer to be able to have enough instantiations of the individual high fidelity molecular dynamics systems to be able to do that effectively. And that's what this parsplice task management system does for Exalt. High performance lamps, MD engines on each node, taking full advantage of the powerful GPUs and their large memories, and then a little bit of overhead to be able to do this careful stitching together of time trajectories. And they got a 500x acceleration over the mirror jet baseline, but this is really an exciting way to be able to do science with MD for a particular problem. We turn our attention to something as passe as nuclear fission. XSMR has also made really effective early use of the machine by doing calculations that are more and more like doing simulations of real, honest to goodness, touch them, knock on them, small modular reactors, sort of from soup to nuts. So not only doing what they call thermal hydraulics, what I would call hydrodynamics, but also the full neutronics in all its glory, and doing that as an integrated application. And I think that the easiest way to talk about this is sort of to see how this has advanced from the time when this project was sort of started on Titan to now on Frontier. On Titan, you were able to do startup calculations. You were basically able to specify a neutron source and then see how the neutron transport happened for some number of pins and some number of particle trajectories. So you're basically solving the Boltzmann equation like a Vlasov equation. So there's no right-hand side. You've specified the source. On Summit, they were able to move to doing what they call full power simulation. So here the source depends on the neutrons that have already sort of been thrown around and transported in the device. But you only had enough power to be able to take snapshots of the state and you had to feed in the thermodynamic conditions that were actually present in the reactor at any given time and take snapshots along. So you could do sort of steady state Monte Carlo simulations of what the reactor looked like at some points along its lifetime. Now Shift on Frontier is able to do a fully integrated, fully coupled simulation of the thermal hydraulics, the things that control the thermodynamics and control the isotopics, that is the composition of the reactor itself, along with a neutron transport solve every single time step. So these same trillion particles that you use to get enough physical fidelity to be able to get a quantitative answer, but do it fully coupled and actually watch it happen in time. That's a decade of work, and that's a pretty remarkable progress towards physical realism and usefulness for engineers in a lot of ways. We also had OLCS sponsored an American Physical Society invited session at the April meeting this year on exascale computational astrophysics. And I invited folks from our ECP engagement projects, so HACK, which you heard about from Lori, I think yesterday a little bit, CHOYA, which is another finite volume hydrodynamics code that's used for galaxy evolution, and Parthenon, which is a COCOS-based AMR framework, and in particular, it's being used in a code called Athena PK, which is has a long and storied history in astrophysical fluid dynamics. This set of codes sort of spans a set of length scales in the universe from hundreds of megaparsecs down to about a kiloparsec or a little bit below. CHOYA is mostly concerned with galactic outflows and galactic evolution on the scale of sort of star clusters. Athena PK is sort of concerned with how those outflows can affect the environment in galaxy clusters themselves. And of course, HACK is sort of interested in large scale structure. I think Lori referred to the notion that it's really interesting with HACK that you're now able to do comparisons to grid-based codes. The most exciting thing from a scientific point of view, I think, is that HACK has added baryonic matter to what they're doing. So if you've ever seen any of these pictures of the so-called cosmic web, the sort of pedagogic lie that gets told to you is that stuff that's glowing, that's all dark matter. It wouldn't glow if it were actually in the universe. That glow comes from stuff that's made of baryons, things like you and me getting heated up. And typically, the way to convert those kind of simulations to something that you can match to observation is to have some sort of semi-empirical way to paint the sky. So given a certain concentration of dark matter at a certain effective temperature, what's the glowing material actually going to look like when you actually see it with a telescope over time? This addition of baryonic matter, again, doing it in a fully coupled fashion at the same time, I think is another real boost that exascale can do. Of course, I'm a stellar astrophysicist, so in my opinion, everything really, really interesting happens off the bottom of this scale plot that I put on that slide. But nevertheless, I think this is a pretty good introduction. Perhaps one of the most interesting projects that we've had on the machine so far is this ALCC project that's been supplemented significantly by DD time on Frontier from GE, looking at full flight scale sized runs of a new open fan concept for jet engines. So it turns out that this open fan concept for jet engines has been around for almost as long as I've been alive, based on what I've read. And it was sort of shelved when oil got a little bit cheaper in the 70s, and there was a real concern about the noise that would be produced by these things. So noise reduction has remained important for these kind of designs. And of course, we want to be able to more and more have more energy efficient ways of propelling ourselves around the planet on jets. This particular simulation has been running semi-continuously on Frontier since we sort of opened it up for open science, and the results that have been obtained are fairly remarkable. The ability to see turbulent eddies, vortex shedding, the impact of turbulence on the velocity field and the pressure field behind the blades of this design at a scale that replicates the full size of an actual engine. So typically these kind of things are done, and you can actually find mentions in the literature from as early as 4 or 5 years ago telling you you'll never be able to do large eddy simulation at full flight scale. Well, we put a lot of that. It's actually been done by this team. And so they have information that can compare to the full flight scale data that they might get later, which makes, running this in a wind tunnel at reduced scale an interesting data point, but not essential to be able to determine whether or not you're going to be able to field this thing or not. This resolving of turbulent scales across orders of magnitude that allow you to understand the behavior of turbulence throughout an inertial range, at least to the scales where it's going to matter for the problem you're looking at. There's no way we'll be able to get down to the viscous dissipation scale where molecules are rubbing on molecules or anything like that. But there are lots of scales above that actually impact the performance of things like jet engines. Again, I think is an essential piece of exascale science. I have to say too, working with this team, has been an absolute delight. They are a seasoned and highly professional set of HPC practitioners. They are, in my opinion, and I'm old and crusty, so I can say this, the old and crusty experimentalist who really knows how to make an instrument sing. And that's exactly what is needed, especially in the early days of a platform. They have pushed through these calculations in the face of lots of interesting things happening on the platform in the early days of its production use. And they've just gotten the job done. It's been a remarkable tour de force from that perspective. So I tried to accelerate a little bit at Christine's behest. So I'll leave my summary up here and maybe just mention this second bullet. I think that resolution and timescales that really enable quantitative understanding, the ability to move beyond the tyranny of periodic boundary conditions, as I said before, and the ability to perform lots and lots of physics at each spatial point, enabling fully coupled multi-physics calculations, calculations that couldn't be done ordinarily in other ways. I think those are the hallmarks of exascale science. And I think, turbulence might be the perfect problem to sort of communicate that to a lot of people. It's something that's important to our day-to-day lives. And we saw, even in this short presentation, I hope you've seen its influence and impact across scales. And watch the space as we're about to onboard several other projects in the coming year. Thanks very much, and I'm happy to take questions.
Thanks, Bronson. Are there questions from folks? It's a quiet group at this point, close to lunch. Thank you very much. Really appreciate it. All right, great, thanks. All right, we'll move on to our last item on the agenda, which is a report on renewing the National Quantum Initiative. So, Charlie, the floor is yours.
Yeah, my slides. All right, thanks for having me. I'm happy to be here to tell you about the National Quantum Initiative Advisory Committee and the report they just released. I'm Charles Stahan. I'm the Assistant Director for Quantum Information Science at OSTP and the Director of the National Quantum Coordination Office. The NQCO has detailees from DOE, NIST, DOD, NSF usually, government detailees who help coordinate the National Quantum Initiative. Just to give you a little bit of background, if you're not enmeshed in quantum, in 2018, the National Quantum Initiative Act was passed by the president after it was passed by Congress. It created some coordinating bodies within the White House, 2 subcommittees that oversee the NQI, the NQCO, the Coordination Office, an advisory committee, a presidential FACA of external academic, industry, and government experts, and it asked NIST to launch an industry consortium. It also asked NSF and DOE to create National Quantum Information Science Research Centers. DOE launched 5, roughly $25 million each. NSF launched 5 Quantum Leap Challenge Institutes at $5 million each. In parallel to that act, the subcommittee on quantum, the interagency, developed a national strategy. It's got 6 key pillars: science, infrastructure, workforce, industry, economic security, and international cooperation. In the last 4 years, we've added to those, to that strategy by doing deep dives into technical areas like sensing or networking or workforce development. So please check those out on quantum.gov. And just real quick, first and foremost, our goal is to get the science right. And that means understanding the applications and timelines where quantum will actually be relevant to our society, and then addressing the technical roadblocks or the quantum frontiers to getting there. And the NQI has had a big impact. It first of all created a national brand for all the quantum activities that have been going on. And in any case, it's spurred a doubling of federal R&D investments. We're about $900 million a year across NSF, DOE, NIST, and the DoD in quantum, created new centers across the country, as I just mentioned. So here's the advisory committee. It's had 2 different forms, one in the last administration, one in the Biden administration. It's a presidential FACA, meaning the president's personnel office finally decides who is on it. So we have roughly 14 members from industry, academia, and government, 2 of which are a part of this panel, Gil and Krista. It's really tasked with doing, first and foremost, an independent assessment of the national strategy, and then recommendations to improve the National Quantum Initiative programs to Congress, to heads of agencies, and to the president. Here are the members. We worked very hard to make it a balanced committee, balanced in terms of technology, in terms of diversity, in terms of geographic diversity. We have computing, sensing, and networking representative. We have 3 large businesses, 3 small businesses, 6 academics, and there's some dual roles here for some of the small companies. I think 3 national lab or federal lab representatives. So I think it's a pretty good committee, and it is the right size for what we needed to do first, which was comments on the NQI in time for the reauthorization. So in the original NQI acts, Congress put a 5-year time window on the reauthorization of the next 5 years of the NQI. And so really, when the NQI Advisory Committee, where the NQI Act got stood up at the end of December last year, our goal has been to basically race to develop recommendations in time to influence what Congress is doing as they pen the update to the NQI. So just for posterity's sake, this is the timeline. In order to create a presidential FACA, you need to create an executive order. We did that. We finally got that out May last year. The members were announced in December. We had our first meeting immediately after that. In the last 6 months, the committee's been working extremely hard to develop a report, which was released a week and a half ago. And this is the report, Renewing the National Quantum Initiative. It's got 3 findings, 4 overarching recommendations, and 9 detailed recommendations. You can find it on quantum.gov if you'd like to read it, but I'm just going to go over the main results and happy to take any questions after. So the main findings, first and foremost, the NQI has increased the capacity of the United States in quantum information science. So its initial goal set by Congress of strengthening U.S. leadership in quantum, the NQI that's a finding of the NQ Act that the NQI has done that. Second, it's the feeling of the NQ Act that the development of Quest is critical to U.S. economic and national security. And third, there are still significant challenges, especially in science, engineering, and systems integration, to overcome, to realize those benefits of this science to the people, ultimately economic and national security benefits to the United States for Quest. So based on those findings, here are the recommendations, the 4 overarching recommendations. Number 1, the NQI should be reauthorized. That was universal opinion of the committee. Many of the centers, took a little while to get started. It was also COVID, and we're just now starting to see the scientific results coming out of them. And it would be a real shame to stop them now. They need to keep going for the next 5 years, even if there's a reconsideration or a recompetition. Number 2, we need to focus on attracting, educating, and developing U.S. scientists and engineers in Quest. The need for talent in this space and adjacent quantum expertise, RF engineering, mechanical engineering, physics, computer science. We have a desperate need for that in the U.S. and everything we can do to increase the number of STEM talent related to Quest will help the country overall. 3, we need to get the balance of economic and national security right. So we need to both promote and protect U.S. leadership in Quest. And part of that means investing in long-term research. So both at the center scale and at the principal investigator level. We have a very healthy system in that we do both, and we do both well. We need to continue to do that and not jeopardize one aspect versus the other. And we have to really invest in our supply chains and understand where our dependencies are and how we can invest in our industry and engineering development to make sure the supply chains are robust so that we can enable the science, but also the future industry and mission applications. And then 4th, and this is really a new thrust for an NQI 2.0, is that we need to focus a little bit more on applications and engineering research, systems integration in the second part of the NQI, because we need to start bringing some of these scientific discoveries to fruition. If we want to show some wins of quantum information science for the country, we need to focus on that. But to do that will require more funding. Every time you increase the technology readiness level of a technology, it's usually a factor of 10 in costs, at least. And I think we just need to be very explicit that needed to happen and that was going to be the result. Okay, so I'm not going to go through all the detailed recommendations. I'm happy to address them in questions. But really quickly, number 1, reauthorize and appropriate the NQI Act. And the appropriate is a key part. If you look back at 2018, in terms of what was authorized, like for example, the NSF centers were authorized at 10 million a year, but they ended up only being 5 million a year. NIST was authorized at 80 million a year, but ended up really not getting any plus up. So following through on our commitments and expanding them as we look to applications, I think is important in the next 5 years of the NQI, and the committee felt very strongly they put that as number 1. Number 2, expand research. I don't think there's any objection from this group. 3, again, try to incorporate industry more in the next phase as we look towards solving engineering problems, systems integration problems, and moving a few technologies from the lab to market. The group really felt that industry needed to be involved more. 4, invest in equipment and infrastructure, particularly in the labs across the United States that have been, I wouldn't say in disrepair, but we haven't kept up with the infrastructure needs across the U.S. 5, keep going with international cooperation. I'm going to talk about that a little more in a second. 6, promote and protect U.S. R&D. strengthen supply chains. 8 is a important one. Developed 8 and 9 are important. The domestic talent piece, the need for dedicated fellowships for domestic talent to create more people here, but equally important to find ways to overcome the roadblocks of getting international talent to come and to stay. There was a significant amount of discussion within the advisory committee on the problems of hiring or keeping foreign talent who are here on visas for school. How do we keep them, and given all the roadblocks? And so there were some specific recommendations around that. So that came out on Friday. We just got it out just in time because the next week, the House Science Committee, which originally authorized the National Quantum Initiative, really championed the National Quantum Initiative, held a hearing where they heard from 5 witnesses from across the quantum community, someone from NASA, someone from University of Illinois, former Undersecretary of Energy, myself, one other person who I'm forgetting, about, really about reauthorizing the NQI Act and how do we maintain American leadership in quantum technology. I will tell you what I said. You can go and watch the hearing. It's quite interesting. All the written testimonies of the attendees were there, but I'll tell you what I said. And this is a combination of what the NQAC's report said. I included that in my written testimony, but also what we internally, through an interagency process, recommended to Congress for the reauth. So first and foremost, again, reauthorize the NSF and DOE quantum information centers, remove the limits on the number of centers so that the agencies could designate more or start new centers based on the science. Like if there's a new idea coming up and you want to make a new center, let them do that. They know what to do. Closely tied to that is, fund them, keep them funded and fund them at the original authorization level at least. Number 2, this is really for NSF as a lead agency, but a message to all is, expand and broaden the participation in quantum information science. In particular, we mentioned a potential for new programs, like mid-career development programs that could bridge the gap from people from other fields to move to this field. Again, trying to address the needs of both industry and government and in academia too, we just need more talent in this space. We need to figure out ways to attract talent, both in the long term, but also in the short term. 3, strengthen the whole government approach. And here this is where we start to really change the NQI or enhance it by adding more agencies. So the original NQI Act only designated activities for NSF, DOE, and NIST. We recommended as an interagency, including the State Department, to run for the benefit of the agencies, an international fund to follow up on quantum cooperation activities that we have started, but have a hard time following through with because there's not enough dedicated funding for international research. We recommended NIH, NASA, and Department of Homeland Security have roles in the NQI as well. And further reiterated, this committee doesn't oversee DoD or IC, but further reiterated that the DoD and the IC are welcome participants in the NQI as well. And then 4, again, just focus on, in the next phase, it needs to continue to be science first. I mean, to continue to think about the long-term problems that need to be solved, but we do need to see some movement on moving some of the discoveries to application. And to do that, our strategy here was really to take advantage of what Congress had already done and just backstop that. Given the environment I think that the country's going to be facing in terms of budgets, there are already large programs authorized in the CHIPS and Science Act and other legislation. For example, $100 million a year quantum networking program at DOE, a $30 to $100 million a year program for quantum user expansion at DOE, the NSF TIP Directorate, which mentions quantum, in the legislation, but It still needs to be implemented. These things were authorized but not funded. And primarily our first recommendation is fund those. And that if you could do that, that almost doubles, our investment. That would be a huge win. And then similarly, a NIST Center for Quantum Engineering, which was actually in the original plan for the NQI, but was never appropriated. So if we could get those as a first go, and the TIP directorate is a huge opportunity, and other similar activities within the Chips and Science Act, which are relevant to DOE as well, for moving science to market with companies and other more engineering centers. I think that's the greatest opportunity we have. Again, already authorized. So really our focus should be on getting those things funded. And then 5, again, highlighting this need to prioritize funding to upgrade infrastructure across the labs in universities and others across the country. 1, to increase the capacity of the US to produce new talents, but also just to remain competitive with the world. If you look at what, for example, the European Union has done during its COVID years, it really revamped technical labs across Europe. A lot of its money went to doing that. We didn't really do that in the US when we had all the stimulus, and it's going to show in a big way, I think, in the next few years. And this is a way to just highlight that. That's all I wanted to say. I'm happy to answer any questions. I've included detailed recommendations for you guys if you want to look at it later.
Questions? So I have one. So what, if I look at sort of where we are in terms of quantum, what do you see as the biggest obstacle? Is it staffing? Is it money? Is it infrastructure? Is it all of those things? And I know the answer is yes at some level, but what's the biggest challenge you're facing?
Yeah, I think if you want to get down it's a global race. We're all trying to find how quantum will benefit, what actual quantum applications will benefit our science or our societies through economy or national security. It really does come down to people. It really does come down to people. And we've seen that, for example, and one of the first things we did when I started was write a report on international talent in quantum, and looked at both and this was in response to the presidential proclamation on visas in June of 2020, which had limited graduate students' visas from China, specifically military fusion schools. And there was concern, like if you extended that to all of China, that would be a lot of graduate students we would lose in this country. It would really affect our ecosystem here. And when we look deeply at what is the US quantum ecosystem, but really the STEM ecosystem dependent on its talent. And for quantum, which is very early stage, it's not stealing the blueprints that will help you get ahead. It's getting the talent. That's what countries are going after. So we need to invest in that. And that happens through research and all the other things we need to do anyway, to advance the technology and the science. But I would say that's the most important.
Okay, thanks. Martin?
What's the sort of industry position on quantum now? Because at one time you couldn't pick up a financial newspaper without seeing an article on quantum, and some company was investigating this. And what's their take on it? And I'm at least kind of partly influenced by, I had one of these strange plane conversations, sat next to somebody who ran a futures company, kind of like a version of the, smaller version of the Rand Corporation or something like that. And she said one of the biggest things that she was worried about was quantum supremacy in terms of what people were asking. So where is the sort of industrial take on all this stuff now? What are you seeing from industry in your interactions, or what are you hearing about?
I think there's still significant enthusiasm for quantum. Over the last 2 years, and basically everything, there's been a significant enthusiasm for high risk endeavors. So we saw some, SPACs in the quantum space. We saw a lot of investment early on. I believe that enthusiasm is still there, but there's a realization of how expensive this technology is now to develop and how slow progress is in real life. You had a lot of VCs come in who thought this thing just happened overnight by Google. Whereas if you look in reality, it was 30 years of government funding that got us to where we were for companies to start taking advantage of that and integrate. And there may be another 25, 30 years, right? And so now the dollar figure is much higher. And so the question is, how are we going to sustain this? And questions about quantum winter and so on. If there is no application discovered, this is for quantum computing. Quantum winter, these are discussions people are having now. What's been underfunded is our applications in quantum sensing, for example, which has near-term applications in timekeeping and gradiometers and biomedical. And we'll see if there's a shift in the funding kind of profile to support that. But I think that's kind of the state of the community. It's still going, there's still enthusiasm, but there's questions about if the global economy keeps going down or there's a lack of capital, how long will the startups, for example, or the big companies continue to support us?
All right, Tina, you're next. Rick, did you still have a question, or is that a? Yeah, I was asking if you. Okay, all right, please.
Hi there. So I'm a quantum researcher in quantum workforce development, but this is my first time in-person meeting. And my overall impression is the people that I work with every day are really going to be quite behind when it comes to all of the science that we're talking about here: supercomputers, artificial intelligence, machine learning, quantum education. And so you talked a little bit about partnerships, but I haven't heard from any of the speakers any sort of suggestion of really how you can have a partnership for education. Mm-hmm. So is that being considered? I haven't read the full report.
Yeah. So one of the it's true, I didn't mention it. One of the things that was authorized in the Chips and Science Act was a Q12. We call it Q12, sort of the K through 12 education funding, sustained commitment to funding to create that future workforce. So that's $8 million a year, which is quite large for education. So that's a great opportunity compared to what's spent now. It is, So that's the first step. The second kind of and third steps are, a big point of the funding for capitalizing labs. When I say expanding capacity of the U.S. to generate quantum talent, what I mean by that is, if you look at where most of the PhDs in physics, frankly, that are now in companies leading the large efforts, they come from the top 25 schools, or maybe the top 15 schools. And that is you cannot scale to an industry based on that. So you need to expand to 100 schools at least, and bring in more technical schools, community colleges, other things that are generating the talent we need. NSF has taken, for example, but DOE is working on workforce development stuff too. But NSF, for example, last year launched the Expand QUIZE program, which is, to me, a kind of a test case at trying to try something different than what's been done over the last 30 years in terms of trying to bring in other schools as leaders and not just followers to the R1 schools to generate talent. But in order to do that, it's not going to be just through R&D investments that NSF makes, small awards. You really need to create labs, and that's going to take significant investment. And that's part of the reason for that recommendation of infrastructure. We need money to buy equipment for people to be trained on. We need money for new labs at universities that can't do it. I mean, this is a personal thing for me. If you look at some of the past programs that have brought in, like minority serving institutions or historically Black colleges, often the programs are led by R1 schools. And what happens is that they identify talent in those schools and bring them there. And so what happens is that it's just limited by the top 20 schools. You need to have 100 schools be leaders to generate talent, but that's really requires some change of thinking and money.
So I agree with you, but I just think I don't think the solutions are unique enough.
Say it again?
I don't think the solutions that people are putting forth are unique enough. So, the partnerships work. You need partnerships because it's really expensive to do research in a lot of these areas. But I think if we need a radical change, I think we should be thinking more radically, right? So I love writing proposals, but I'm still competing with some top institutions.
Yeah.
So
I have a whole bunch of ideas on this. I mean, one of the things we wanted, it's on our list to do in the NQCO, is to hold the uncomfortable education workshop. And talk about some of these issues. So, for example, I'll give you one that the NQAC addressed in their report, and more sub bullet is, if you look at how NSF funds broader impact research, it asks every professor getting a grant to spend some portion of their money on broader impact. And now what most professors do is just make a web page or something some are really into it and do a great job, but some are just not suited for it. So one of the recommendations was, well, what if we pool that resource of talent and have it be led by people who actually know what they're doing in terms of education, right? Could that be a more effective way? That's just an example. There's more radical things you could do, but I think we need to get those to the surface, because frankly, they are sometimes uncomfortable because the agencies they've done it this way and they have a viewpoint, and this would potentially upend how they're doing things.
Yeah, I'll just say one of the broad issues that we're talking, I would say that as the country thinks about expanding the diversity and the numbers of people in STEM domains, I mean, we're short millions of people. And it does have to be a much broader base. And yeah, I agree with you. I'm wearing my other hat as chair of the National Science Board now. When I say this, we've got to think in some different ways about how we change this game, because it can't just be the top 20 universities that we're talking about. Talent comes from everywhere. Ed.
Thanks. On the same topic, actually, just to give you a sense of experience I have now from the University of Wyoming. I recently moved there from University of Illinois, which is top notch in this area. And so our physics department did get one of those new NSF Expand QISE grants. And so that's been a big shot in the arm there. They are still thinking about quantum materials and not about supercomputing. So they're a really long way, kind of to your point, about thinking about how to actually build this stuff. At the same time, I went down to the Front Range in northern Colorado, kind of around the Boulder area, where there are lots of quantum companies popping up. And so, now some of them have announcements of machines and so on. They're desperate for community college trained technicians. And so they wanted to help us build a relationship with Wyoming community colleges, which I found really interesting, kind of to this broader topic. So they're being held back by just having people who are able to build things on circuit boards and stuff like that, and so that's really important. But I have a relationship with all the community colleges. In fact, with all the presidents of the Wyoming community colleges, we meet regularly, trying to convince them that they should invest in a program in quantum information science when they're doing welding. I mean, it's hard to communicate this, but this is the magnitude. It's kind of a sociological problem to get this thing off the ground. So I'd be happy to share some ideas on that later.
Okay, yeah, great.
Any other questions? Thanks, Charlie. Really appreciate it. All right, that's the end of our formal agenda, other than whether there are any public comments. So anybody want to offer any comments, either the committee or from the public? I'm now standing between you and lunch. I do recognize that. Well, this has been a really meaty set of discussions and some really challenging issues before us. We're surrounded by opportunities. That's the optimistic way to look at it. But I will just reiterate what I said at the outset. We've got to find a way to elevate the discussion about some of these national issues, because they really do affect the future of the country. So welcome ideas about that. Remember Christine's plea to respond about potential dates for the September meeting, and think about ways we can leverage our influence to pursue the best interests of the country. And with that, as my grandfather used to say, go and sin no more. We're finished. So thank you all.